Okay, so we will continue with the virtual memory discussion. So we were seeing the page replacement algorithms. We have seen the FIFO page replacement algorithm. So in the FIFO algorithm, basically you were removing a page that has been brought into memory first, right? So first in, first out. The first page that has been brought into the memory first, that has been brought into memory, it will be removed first, okay? The first page that is brought into memory will be removed first. So basically you remove the oldest page among the pages that are in memory. So we have seen that FIFO has an anomaly. So normally we expect, if you increase the number of frames, we expect that the number of page faults will decrease. And this will happen most of the time. But from time to time, you may see such an anomaly where you increase the number of frames, for example, but you see more page faults for some reference strings, okay? So you can observe such an anomaly. But most of the time, you should not see that. Most of the time, you should see that the page fault rate is decreasing while the number of frames are increasing, okay? So this was the FIFO algorithm. Do you have any questions about the FIFO algorithm? So it's very simple, right? The page, among the pages in memory, you remove the page that is the oldest, okay? And the problem with that approach is this. For example, you may have a page to remove, for example, here, when this reference is made, okay? So it's already in memory. But when this reference is made, so it is not in memory, so you will remove one of those pages. Which one is the oldest here? 201. Which one is the oldest? So 0 is oldest, so you remove that, okay? But actually, it might have been referenced very recently, okay? You are just looking to the time that the page is brought into memory. You are not looking to the time that it was referenced last, okay? So basically, you may remove a page that is heavily used, that is recently used, but that page may be an old page, and you may remove that. Therefore, this approach in its pure form is not very good, but a modified version of that can be used, okay? So the second algorithm that we will look is the optimal algorithm. Now, we give you an algorithm, describe you an algorithm that is optimal, that causes least number of page faults. So what is the idea? Now, whenever you would like to replace a page, remove a page, you select the page that will not be used for the longest time period towards the future, okay? So in this way, you are trying to defer the page faults as much as possible towards the future, okay? You are deferring the page faults. So this is the approach. For example, assume we have 4 frames, and this is the page reference string. So what is happening? 1 is reference, so it is brought into memory. This is a page fault. 2 is brought page fault. 3 page fault, and 4 causes also page fault, right? Initially, all the frames are empty. Then 1 is referenced. It is already in memory. 2 is referenced. It's already in memory. 5 is referenced here, okay? Is it in memory? No. So we have to remove one of the pages. Which one would you remove according to this algorithm? Now you look to the future. Which one of those pages will not be used for the longest time in the future? So you are here. Which one of those pages will not be used for the longest time? 4, right? 1 will be used soon. 2 will be used quite soon, and so on. But 4 will not be used for the longest time in the future. So we remove 4 and we put 5 in place of 4, okay? So this is the basic idea. So then, for example, after 5, you reference 1, it's in memory. Reference 2 in memory. You reference 3, it is in memory. Now you reference 4, for example. Is it in memory? When you reference 4 here? No, it is not in memory. So you will remove one of the pages. So which one of the pages here is the one that will not be used for the longest time in the future? You don't have that information at the moment. So you can select one of them arbitrarily, or you can select, for example, the page that is oldest. Which page is oldest here among those pages? So 1 is oldest, right? So you can remove 1 and put 4, for example, instead of 1, and so on, okay? So this is the basic idea. Or you can use another tie-breaking rule. So this is the optimal algorithm. This is the algorithm that provides the minimum number of page faults. No algorithm can beat that, okay? But the problem with this algorithm is that it requires you to guess the future, which you cannot guess easily, okay? Which you cannot know. So therefore, this algorithm is not very practical. But it has theoretical importance. You can actually use that for comparison purposes. You can develop a practical algorithm and compare your algorithm's performance against the performance of this optimal algorithm. So the use of that algorithm is that, okay? to compare some other practical algorithms against this algorithm. Is it clear? So this is the optimal algorithm. So this is another example for the optimal algorithm. So this is a reference string, page reference string. We are referencing page 7, then page 0, and so on. So initially all the frames are empty. We have 3 frames. So 7 is brought into memory. This causes a page fault. This causes a page fault. That causes a page fault. And we access 2 here. It is not in memory. So that also causes a page fault. So which one among these pages you remove when 2 will be brought into memory? You look to the future. Which one of those pages will not be used for the longest time in the future? So 0 will be used here, 1 will be used here, but 7 will not be used up to that time. So 7 is the one that will not be used for the longest time, right? So therefore we remove 7 and we put 2 in place of 7 and we continue like this, okay? So this is the optimal algorithm. Then you can trace the algorithm on such a reference string and find out which references cause the page fault. This reference causes that, and what else? This causes a page fault and so on. That causes a page fault. This causes a page fault and so on. So then you can count the number of page faults and understand what the performance of the algorithm is. Is it clear? So this is the optimal page replacement algorithm. And now let's look to a more practical algorithm. Optimal is not practical. So a heavily used algorithm that is also practical is the least recently used algorithm. Okay, this is a good algorithm. So it actually performs well. And this is the idea. Now whenever you would like to replace a page, okay, you look to the pages in memory and you select the one that is least recently used. Okay, that is least recently used. That is not used recently. Okay, you do not select a page that is recently used. You select a page that is least recently used. Okay, so for example, assume we have that reference string. So initially memory is empty, 4 frames are empty, so this causes a page fault, that causes a page fault, and those 4 pages are loaded into memory. Then 1 is referenced, it is in memory, 2 is referenced, it is in memory. Now you reference 5. You would like to access page 5. Is it in memory? No, right? So you want to remove one of those pages and put 5 in place of that. Which one would you remove? So according to this algorithm, now you look to the past and select the page which is least recently used. Which one of those pages, 1, 2, 3, 4, is the one that is least recently used? 2 is quite recently used. 1 is quite recently used. 4, 3 is actually the one that is least recently used among those pages in memory, right? So therefore you select 3 and remove that and put 5 in place of that and continue like that. After 5 you reference 1, no page fault. You reference 2, no page fault, and you reference 3. So 3 is not in memory, so you would like to remove one of those pages. Which one is the least recent one? So 4 is the least recently used one, right? So therefore you remove 4 and put 3 in place of that and so on, okay? So this is the basic idea. Now in this LRU algorithm you look to the past, not to the future, okay? And it's practical. So if you trace this algorithm, you will see that each page faults will happen for this page reference string, okay? For the same string you can look, for example, how many page faults will be there if you use optimal algorithm, okay, or 5 algorithm, and you can then compare the algorithms. Any questions? So this is another example that shows, that traces the execution of the least recently used algorithm on a reference string. So this is a reference string, for example. So we load 7 into memory, then 0, 1 into memory. These 3 references causes page faults. Then you try to load 2. So 2 is not in memory. So which one of those pages is the least recently used one? 701, which one? 7, right? So you remove 7 and put 2 in place of 7, and 0 is in memory. 3 is not in memory, so it will cause a page fault. So you will remove one of them. 0 is the least. Which one is the least recent used one? 201. At the time that you are accessing page 3. Among those pages, 201, which one is the least recent used one? 1, right? So you remove that one and put 3 in place of that and so on, and then you can count the page faults here. So how many page faults are there? 4, 5, 9, 10, 12 page faults, right? So this is the working of the algorithm. This is how the algorithm works, but how can we implement it? Okay, let's look to that issue now. How can we implement that algorithm so that the system behaves like that? It selects the page that is least recently used. So how can we implement that? We will now look to that. We will see 2 exact implementations of the LRU. Those implementations are actually selecting the page that is least recently used, okay? the page that's selected is really the least recently used one. So how those implementations work? We see counter implementation and stack implementation. So in counter implementation, we do this. Every page entry, every page has a counter associated with it, okay? Every time you reference a page, okay, you access a page, you just update that counter value with the current clock value. In the computer, you also have a clock hardware, okay, that is ticking, that is always incrementing, okay? It can be just an integer that's always getting incremented with every clock cycle, for example, okay? So assume you have such a clock device, and whenever a page is referenced, you copy the clock value to the counter field of the page, okay? Maybe that field is just as part of the page table or in some other kernel data structure, okay, that's maintained for the pages. So then you copy, whenever a page is referenced, you copy the clock value to the counter associated with the page, right? So the pages are referenced, and whenever a reference occurs, you perform this operation. So now, when a page fault occurs and you would like to replace a page, then what happens? You look to the pages in memory and their counters, and you will select the page that has the smallest counter or the largest counter to remove. Which one has to be removed? Smallest, right? Because this is the page that hasn't been accessed for the longest period of time. That is the least recently used one, okay? So we are looking, be careful, we are not looking to the time that the page is brought into the memory. We are not looking to the age of the page. We are looking to the reference time of the page, when each page is referenced last, okay? Then we make a decision based on that. Not, for example, when the page is brought into memory. We are not looking to that information. That information is looked by whom? By the FIFO algorithm, right? We are looking here to the time that the page is accessed last. And we remove the page that hasn't been accessed for the longest period of time, okay? That is the least recently used page. So this is one possible implementation, and the other implementation can be stack implementation. Basically, the name is stack, but it is not exactly a stack. So we use a data structure holding the pages. So pages are linked, okay, together. So basically, this can be also called linked list implementation. So we have list of pages that are in memory, okay? This can be a double linked list. So whenever, for example, you reference a page in that list, okay, in memory, you take the page and put it to the head of the queue, or head of the list, or top of the list, okay? So basically here, assume this is the page reference string, and you are around here in the execution. So you would like to reference page 7, for example. And just before that reference, this is the page, these are the pages in memory. You have page 2, 1, 0, 7, and 4 that are linked together, okay? That make a queue. So this is the head of the queue, and this is the tail of the queue, or you can consider it as a stack. This is the top of the stack, and this is the bottom of the stack, okay? So when you reference page 7, okay, then you immediately search for 7 here and take 7 here and put it into the top of the stack, okay? So take 7 from here and put it to the top. So after 7 is referenced, then this will be the state of the stack. So 7 becomes to the top. And if you do this with every memory reference, every page reference, what will happen? At the top of the stack, you will see what? You will see the page that is most recent accessed, right? And at the bottom, you will see the page that is least recent accessed, okay? So then it is very easy at the time of a page fault to select a page to remove. You will select the page at the bottom of the stack, okay? It will be removed. This is not exactly the stack that you have seen in CS-342, but it's a similar idea, okay? So then, this is the basic idea. Whenever a page fault occurs, it is very easy to select a page to remove, right? But what is the difficulty here? What is the cost here associated with this implementation? With every memory reference, page reference, you have to search the list, find the reference page, and move it to the top. And moving it to the top, actually, you are playing with the pointers of the linked list here, right? You are breaking the pointers here, and you are adding it here, and you are making the pointers links here, and so on. So basically, all these pointers are memory references, right? So that means you are making quite a lot of memory references, 5, 6 memory references to update the list. With every memory reference, with every page reference, you actually make some more memory references, which will slow down the system, okay? This increases the number of memory accesses required to execute the program. Therefore, it is not very efficient. But here, this page that we are selecting is really the page that is least recently used. Okay, so this is an implementation that is implementing LRU exactly. Okay, so it's an exact implementation, not an approximation. But it is costly. So these two implementations are, stack and counter, are exact implementations of LRU, but they are costly, right? So can we have an implementation that is less costly? That implementation will not be an exact implementation, but will be an approximation. So we will now see some approximations for LRU, some algorithms that approximate LRU or use the same idea with the LRU, but it's an approximate. That means the selected page may not be the exact least recently used page, okay? But it is least recently used, okay? It will be a less recently used page, but may not be the least recently used, okay? So let's look to the approximations. How can we approximate? We will now first see a very crude approximation, okay? So in that algorithm that is approximating LRU very crudely, we use a reference bit for each page. So we associate a reference bit, one bit of information to the page. So that bit, for example, can be stored in the page table. So in the page table, you have an entry for each page. As part of that entry, you have the frame number, right, where the page is stored. You can have a bit indicating the reference bit, okay? That will be used for this purpose. Whenever a page is referenced, okay, you set that bit to 1, and it stays 1. So further references will do the same thing. That means when it is set to 1, it will remain 1, right? Until when? Until, for example, periodic clock interrupt arrives. Periodically, every 10 milliseconds, 20 milliseconds, hardware interrupts, right? Clock device of the timer device interrupts. So then an OS routine is run, and that OS routine will clear those reference bits, okay? Will clear those reference bits. So now, when a page fault occurs, okay, you want to select a page to remove. So which page should be selected? So you will see now some pages whose reference bit is 1, some pages whose reference bit is 0. Which one would you choose? One of the pages whose reference bit is 0, right? That is, it is not accessed during the last clock interval. After the operating system cleared out all the reference bits of the pages, then again system continues. Page references are made until the next clock interrupt, which may be 20 milliseconds later. During this time, the system can make lots of page references. So for those pages, the reference bits will be again set, right? So next time the clock interrupt arrives, you will see that some of the pages are referenced, some of the pages are not referenced during the last clock interval, okay? So this is the normal operation of the system. So when a page fault occurs, at that time, you will see that some of the pages are referenced, their reference bits are 0, some of the pages are not referenced, their reference bits are 0. So then you will select a page whose reference bit is 0. Okay, that means that page has not been accessed since the last clock interrupt. Okay. So this is, of course, a very crude approximation. You can have lots of pages whose reference bits are 0, and you select one of them. Okay. And you don't know exactly which one is the least recently used one. You don't have that information. You just have this information that those pages are not referenced during the last clock intervals. Okay? You just have this information and you make your removal based on that information. Is it clear? Therefore, it is approximating the LRU very crudely. Okay? So now let's look to another algorithm, second chance algorithm. Okay? So this is an adaptation of the FIFO algorithm that uses the reference bits. So it's a combination of this algorithm, okay, and the FIFO algorithm that we have seen earlier. So let's remember the FIFO. FIFO algorithm is a first in, first out algorithm, right? So it can be implemented using a queue, actually, queue of pages. So whenever a page is loaded into memory, it can be added to the queue, tail of the queue, right? That means it will be the youngest page. So if you do this, at the end, you will see a queue of pages in memory, right? So those are the pages in memory. So whenever a page fault occurs, you would like to remove one of them. Which one you would like to remove? If you apply the FIFO algorithm, you will remove the one that is oldest. If you look to the queue, which one is the oldest one? Head of the queue, right? because whenever a page is loaded, you just add it to the tail. All right? So head of the queue is the oldest one, okay? So all the new pages are added to the tail. So for example, then you will replace that one, okay? You will replace that one. So basically, so that page will be removed and a new page will be added to here, okay? So this can be the, for example, the FIFO algorithm. So now you apply the same algorithm, but this time you use the reference bit, okay? So whenever a page fault occurs, you start searching for a page for removal from the beginning of the FIFO list, okay? So if the reference bit of that page is 0, you are done. You select that page and remove that. And you add the new page to the tail of the queue, okay? But you use the frame that that page was in, okay? So, however, if the reference bit of that page is 1, the head of the queue page is 1, that means now that page is actually quite recently accessed in the last clock interval. So it is not a very good candidate for removal. So you give it a second chance. You just change the reference bit to 0 and move it to the tail. Okay? This is what you do. So you don't remove that page, but you move it to the tail. You give it a second chance, but you actually set its reference bit to 0. Then you look to the next page. All right? You look to the next page if its reference bit is 0 or 1. If it is 1, you do the same thing. That means it's also quite recently accessed, so you would like to give a second chance. So you just set the R bit to 0 and move it to the tail. You make it the youngest page, okay? So that it will not be removed for a while. But then you do this until you find a page whose reference bit is 0. That page is not recently accessed, okay? And it is now quite old as well. It is close to the beginning, so you remove that one, okay? So this is the basic idea, the second chance algorithm. Basically, it's a FIFO algorithm where the pages are given a second chance if their reference bits are 1. Why second chance? Because assume if all the pages have their R bits 1. Okay, so you have now in pages in memory, all of which are accessed quite recently. So you start searching for a page to remove from here. You see the R bit as 1, so you move it to the tail. So R bit of that page will become 0. And you do the same thing with the next page and so on. Finally, what you will have a queue of pages, right, whose R bits are all zeros, right? Now this time that page will be removed. Okay? That page will be removed. You are not giving another chance. Otherwise, you will not be able to find a page to remove, right? So this is the second chance algorithm. If a page is to be replaced, we look to the FIFO list and we remove the page close to the head of the list and that has a reference bit 0. Is the idea clear? So in this way we are improving the FIFO algorithm a little bit because we are not removing a page that is oldest but that is also recently accessed. Okay? So a heavily used page is tried to be kept in memory. So you can actually implement this algorithm in a different way, in a more efficient way. Then this algorithm becomes a clock algorithm. So the second chance algorithm, if you change the implementation of that, then the new algorithm has a new name, which is the clock algorithm. But the idea is the same thing. FIFO together with the reference bits is this algorithm, clock algorithm. So now what we have a set of pages now that are connected together as a linked list that is circular, okay? A circular linked list. So that means we have something like a clock here, and we will traverse this in the clockwise or counterclockwise, okay? So at any time, we will have a pointer or hand pointing to one of those pages, okay? That page will be considered as the oldest page, all right? Initially, it may be this page, but we will advance it with the mechanism that we will describe next. So at any given time, if you look to the circle list of pages, you will see that the hand or pointer pointing to one of those pages, assume this is the page pointed by the hand now, okay? So whenever a page fault occurs, you will start searching for a page for replacement from here, okay? So you will inspect that page first, and you will try to remove that one first. That means this is the oldest page, okay? And so this is the head of the queue, this is the tail of the queue, okay? So you will start inspecting from here and continue like that. So you will try to remove that page. you look to its reference bit. If it is 1, you do not remove it. Okay? If it is 0, you just immediately remove it. Okay? You just immediately remove it, replace it, and put a new page into its frame. But if its reference bit is 1, what you do? You do not remove it. You give it a second chance. You just move the hand by 1. So that hand points to the next page here. Okay, so you examine this page now, its reference bit. So that means this becomes the tail of the queue in the FIFO. Okay, so next time it will be examined will be after you all scanned all these pages. Okay, so basically by just having a hand traversing the list, you don't have to update the list like here, for example. You don't have to take this and put it there and so on. Okay, instead of doing that, instead of removing the head and putting it to the tail, you just move the hand, which has the same effect. By just moving the hand from here to there, you make this one the head, and this will become automatically the tail, right? And if you move the head one more, this will be the head of the queue, that will be the tail, right? So hand is moving like that. So you inspect the next page. Its reference bit is 0 or 1, right? So that means it is also recent access, so you don't remove it, right? You give it one more chance, so you move the hand here. But before doing that, you actually set those bits to 0 again, as in the previous algorithm. So whenever you see the reference bit as 1, you do not remove the page, you look to the next page, but at the same time you change the reference bit to 0, okay? Next time, if you come to here again, you will see the reference bit 0, okay? And that page will become a candidate for removal. So you continue doing that in clockwise or counterclockwise fashion or order until you find a page whose reference bit is 0. So in this case, this will be that page. So you remove that page, okay? So the frame holding that page will become empty, and you will put the new page into that frame, okay? And you will make the hand pointing, for example, to the next page, so that after that, the next search will start from here and so on, okay? Is the idea clear? So do you think that this algorithm will terminate? Definitely you will find a page for removal or not? Can we have such a situation where we will just look around, and we'll never find a page for removal? No, why? Right, exactly. Because we are changing the bits here to 0, so next time, if all the bits are 1, right, we will continue scanning the pages, but we will come back to here and see that the reference bit is changed to 0, so we can remove that, okay? So if we start from here and all the bits are 1, okay, assume all the bits are 1 and we start from here to search. So while searching, what were we doing? We were looking to the page, reference bit. If its reference bit is 1, we change it to 0 and look to the next page, right? So while you are scanning those pages, you are also changing the reference bits to 0. So then you will just make a circle around these pages and will come to here and see now this time the reference bit of that page is 0 and you will remove that page, okay? So it will degenerate to FIFO actually in that case. So this algorithm will definitely terminate and will find a page to remove. Is it clear? So this is the second chance algorithm. So besides those algorithms, we have some other algorithms, counting algorithms. First, starting for them, let us repeat that the second chance and the LRU approximation with reference bit, they are actually a combination of LRU idea and FIFO idea. Okay, this is, for example, a combination of LRU idea and FIFO idea. Why FIFO idea? Because we have a linked list of pages or circle list of pages, and the pages are added to here, to the tail of the queue. Any page is added to the tail of the queue. Okay, if everything is equal, if all the pages are referenced or unreferenced, then we remove a page that is oldest. Okay, so we have the FIFO idea here, plus we have the LRU idea because we look to the reference bits. A page that is recently accessed is not removed. A page that is not recently accessed is removed. That means a page that is less recently used is removed. Okay, it is trying to approximate the LRU. Now we will look to some other algorithms, counting algorithms. So what we can do is this. We can also associate a counter with every page so that whenever a reference occurs to that page, the counter value is just simply incremented. With every reference to the page, you increment the counter. Okay? So after a while, you will see what? You will see some pages in memory and their counters, and the counters will have associated values, right? So now you can do this. Whenever a page fault occurs, you can select a page that has the least counter, smallest counter, or largest counter. Okay? So which one would you do? You can do both, and you can have an argument for both. For example, for the smallest, y, you can argue like that. I remove the page who has the smallest counter because that is not very frequently used. Okay? A page that has a very large counter value means that that page is heavily accessed. Okay? So I don't want to remove that. I will remove the smallest counter page. So this may be a valid argument. But actually, we may also have a counter argument against that, like this. So a page may be loaded into memory, for example, 3 days ago, and initially it might have been accessed very much. Okay, so it may have a very large counter value, but for 2 days it is not accessed. Okay, and then another page that is recently brought into memory is accessed, but its counter value is smaller, but it will be accessed more, right? So in this case, you are removing actually the second page that is brought recently. Okay, that is a small counter value. But actually, you should not do that because that page is going to be accessed soon again, right? So you can have arguments like that as well. So basically, you can have also MFU algorithm. The first algorithm where you select the page with smallest counter, it's called least frequently used algorithm, LFU algorithm. If you select the page with the largest counter value, then it's called most frequently used algorithm. You select the page whose counter is the largest for removal. Okay? Why you can do that? Because you can argue like this. A newly brought page into memory, initially when you brought a page into memory, its counter is initialized to 0, right? So a page, for example, that has a small counter value will be a page that is new, that is newly loaded into memory. So it will be accessed quite a lot. It's not an old page. So because you need that, okay, you brought it and you will use it. So you may argue like that, and you may try to keep such pages whose counters are small in memory. And you may want to remove a page whose counter is large from the memory because that page is quite long. Okay? We have used that page long enough, so probably we will use some other pages and that page will not be used. We may argue like that, and we can remove such a page whose counter is quite large. Okay? So then that algorithm is called MFU algorithm. Any questions so far? So now let's look to a different issue. So far we have discussed how we can remove a page, okay, if we would like to load a new page. So for that we made such an assumption implicitly. A process has been allocated a set of frames, let's say 10 frames. So the process is making page references, and those pages are brought into memory and put into those 10 frames, okay? So assume those frames are filled up. So a process would like to access any page that is not in those frames. Then what you do, you go to the disk and bring that page and put it into one of those frames. For that, you have to replace the content of one of those frames, of course. All right? You remove a page first, and then you put the new page into the frame of that page that is removed. So far, we have assumed that we somehow allocate some number of frames to each process. And we have discussed how those frames can be utilized by the process using page replacement algorithms. Okay? Even though, for example, a process allocates just 10 frames, it can actually make references to 100 different frames. Only at a given time, you have to keep 10 of those 100 pages in memory in those 10 frames, right? By replacing the pages, you can do that, right? Now, this is the question. How many frames should we allocate to a process? We said that we can allocate just 10 frames, but how do you decide on that? All right? So we will now look to this issue. For that, we actually look first to this issue. What is the minimum number of pages or page frames that has to be allocated to a process in order the process runs? So that the process can run. That depends on the architecture. For example, assume we have a computer, all right, that has such an instruction, move instruction, okay? that just moves one memory variable into another one. Okay, so it makes a memory access, gets the content from there, and moves the content from another memory location, right? So basically, it can take two memory operands, two memory addresses, and it moves the content of one memory address to the content of another memory address. Okay, so basically, for example, it may try to move just 8 bytes of data from here to there. The integers may be 8 bytes long. Okay. So, however, an integer may be located at a page boundary. Some part of the integer may be in this page, some part in the next page, right? This is possible. That means the integer value may span 2 pages. The source operand may span 2 pages. The destination operand may also span 2 pages, right? This is possible. That means in order to move this value from here to there, you need to access 4 pages. This is possible, right? Plus, you have to actually, the instruction itself is sitting on the memory, on some page, or maybe at the page boundary. If the instruction is just, for example, 4 bytes or 6 bytes, okay, what can happen is 3 bytes may be in one page, or 2 bytes may be in one page, and the remaining 4 bytes of the instruction may be in another page. Instruction may be just sitting on the boundary of 2 pages. It is possible, right? So if this is the case, if the program is actually located in the physical memory like that, okay, and logical memory like that, then that means in order to run such an instruction, we need actually 6 pages to have in physical memory at the same time. 2 pages for the instruction itself, 2 pages for one operand, 2 pages for the second operand, source operand, destination operand, okay? So in order to have that instruction to execute properly, you need to have 6 pages in memory. If you do not have all these 6 pages in memory, then that instruction cannot be executed. Why? Assume you start executing that instruction. All right? So assume just 2 pages are in memory, which contain the instruction. You start running that instruction, executing instruction in the CPU. It will make a memory reference to fetch the operand. There you will have a page fault because the pages holding the operands are not in memory, right? You will have a page fault, so OS routines will get executed to get the pages from the disk, load them into memory, okay? After that operation is finished, what do? The page fault handler is restarting the instruction, okay? So if it restarts the instruction, that means you start from the beginning. So again, if you do not have all these 6 pages in memory, you will encounter the same problem, okay? So unless you have all these 6 pages in memory, you will just continue faulting at the same instruction, okay? So therefore, in order to be able to execute that instruction, we need 6 pages physically ready in the memory, all right? So that means you have to allocate at least 6 pages, page frames, to such a process. So therefore, the minimum number of pages or frames to be allocated to a process depends on the architecture and the complexity of instructions and so on. But that is not the only problem that we face. So let's assume that every process has that minimum number of frames allocated. Okay? But you may have a huge memory. So you have lots of frames. How do you allocate the remaining frames to those processes? Okay? So for that we see 2 major allocation schemes. One is a fixed allocation, the other is a priority allocation. So fixed allocation is this. You allocate fixed number of frames to each process. What is that fixed number? It may depend on the size of the process. Or it may be just an arbitrary number. So equal allocation means this. There may be 100 frames in memory. And there may be, for example, 5 processes. You can just divide 100 by 5 and obtain 20. That means you can just give 20 frames to each process. This may be one allocation strategy, right? So each process in memory will get 20 frames and they will continue running. So this may be one allocation scheme. But the problem with that is that some processes may be small, some processes may be large, and this is not very fair for those large processes, right? All processes will get the same number of frames. This is not fair. So then you can apply a proportional allocation scheme where you can allocate number of frames to the processes depending on the size of the processes, okay? If, for example, the size of a process Pi is denoted with Si, okay, then the sum of sizes of all processes is S, okay? So then the ratio of the size of a process to all the sizes, sum of the sizes, will be Si over S. You give frames to a process depending on that ratio. So if M is the total number of frames, then a process I will get that many frames. Size of I over total size of all processes, right? Multiplied by M. M is the number of frames. So each process then will get that many frames. So if you do an example, assume there are 64 frames in memory, physical frames available, 64. And assume we have two processes. The size of one process is 10. The size of another process is 127. Okay. So now, what should be the number of frames allocated to process 1? The number of frames allocated to process 1 will be 10 over, total size is 127 plus 10, which is 137. 10 over 137 multiplied by 64 will give you 5. So 5 will be the number of frames that are allocated to the process 1. Okay? Process 1 should be allocated 5 frames. The other process whose size is 128 will be allocated how many frames? 128 over 138 to 37, sorry, multiplied by 64, and this will make around 59 frames. So the second process will be allocated around 59 frames. Okay? So in this way, you are allocating frames to the processes that are, the number of frames are allocated to a process is proportional to the size of the process. Okay? So here actually, you are utilizing the length of the process as a priority. So you can make a priority-based allocation. So we can use a proportional allocation scheme using priorities rather than sizes. So again, you will apply a proportional allocation scheme, but the priority is not depending just on the size, but it can be depending something else. So proportional allocation will depend on the priority of the process, which may depend on something else other than the size. If process PI, for example, generates a page fault, that means process PI needs a new page. Then what you can do, you will select a frame, and you will remove the page existing in that frame, right? And you will place the new page into that frame. So now what you can do is, you can select a frame belonging to a process with a lower priority. You can do that. That means you are taking a frame as a process who is faulting. You are taking a frame from another process who has a lower priority than you. Okay? In this way, the priorities will affect how many frames the process will have. Okay? This is another allocation strategy, priority allocation. Another issue is this. While allocating the frames to the processes, if a frame is to be allocated, okay, initially, for example, each process has been allocated a set of frames. All right, a process faults. Would you allocate a frame to that process from its set, own set, or can you consider all the frames in memory and select one of them as the victim frame, make it empty, and put the new page of the process faulting into that frame? If we apply the first strategy, that means each process selects from only its own set of allocated frames to replace a frame, okay, then we apply a local replacement strategy, that means, okay. So assume you are a process, you have given 10 frames, all these frames are filled up with your pages. You again need a new page. Now you will select one page for removal. If you just consider your own frames for removal, to remove a page, then that means you are applying a local allocation strategy, okay? Local replacement. In the global replacement, the process selects a replacement frame from the set of all frames in memory, okay? And those frames may belong to some other frames. In this way, a process that needs a frame may grab the frame that is belonging to another process, okay? So if the allocation strategy and replacement strategy is working like that, then this is called global replacement, okay? So in this way, one process can take a frame from one another, okay? When I need a frame, I can, for example, make empty one of my frames, or a frame belonging to somebody else can be made empty, and my page may be loaded there as well. Then that frame will belong to me, okay? So this is the global allocation scheme. So we will stop here and take a break, and then we will continue.